So this exercise related to Doppler effect and the pulse echo. First 15 questions I have solved, so I will do from question 16. So first we have question 16 is there. As you can see, the graph is there for the frequency, which is received. A spectator at a motor race record a frequency of a sound he hears as a racing car driving past on a straight path. So you can see different frequencies are there. The graph shows how the frequency of a sound he hears vary with time. The car passes a spectator at time x. So this is a point where the car passes the spectator. And that will be the frequency at which it passes. Explain the shape of a graph. We have to explain the shape of this graph. First, you can see like the say this is a position like this is the position x is there where the spectator is observing a car. So when he is like this is the frequency of a sound he received. So you can see here when this car was approaching or moving towards the spectator, the frequency which the spectator frequency of a sound which spectator was receiving, that was higher. But as the car is moving away, the frequency decreases. So if frequency decreases, the wavelength increase, it means it is moving away. But it's a 4 mark and you have to explain the points, and you should write the answer in appropriate like logical manner. Like things should be related to each other. When you finish like writing one sentence, the second sentence should relate with the first sentence. First thing, why there is a change in frequency? First thing you will mention that is due to the Doppler effect cause the change in frequency, which is received by the observer. And before point X, like this is a point, say this was point X. So before point X, the car is moving towards the observer. That's why the frequency was higher as compared to when the car is moving away from the observer, the frequency will decrease. But the speed at which the wavelength, the speed at which the wave is moving, that does not change, because here what happened, as the car is approaching point X, the frequency was higher, the wavelength is shorter. But when it is moving away from it, the wavelength frequency was shorter, but the wavelength is longer. And exactly at point X, like point X is a point where the observer was observing. So at point X, they have a minimum distance between them. So it means at point X, the frequency which is received by the observer will be same as the frequency of a sound emitted. All the places like here, when the sound, say maybe the sound which is emitted out, sorry, maybe the sound which is emitted out here might be 1000 hertz, the frequency of a sound. But what observer will receive, the observer will receive 1200 hertz. But and same thing at this point, because it is moving away, the frequency emitted out, frequency of a sound produces 1000. But what is received, that will be shorter, like maybe 950 hertz. But at point X, the frequency which is emitted out from the source will be same as the received by the observer, because they are very close to each other, or like negligible change, reference change is no change is there, or net change. So the points you will mention here, the 4 marks. So the first point, the change in frequency is due to the Doppler effect. And before point at X, the source was, or the car was moving towards the observer. So frequency was high and wavelength was short, which is received by like frequency and the wavelength upper end. It's not like the frequency and wavelength changes from a source. So what is received by the observer will change only. So before point X, the car was moving towards the observer, so frequency was high and the wavelength was short. At X, the frequency emit from the source is same as observer or what is received by the observer, but after point X, so the car was moving away from the observer. As a result, the observer will receive or will record the short frequency and longer wavelength. The speed of the wave does not remain constant. The speed of a wave does not change because it is given by a formula V is equals to F. Like speed is equals to frequency times wavelength, so V is equals to F lambda. So if the frequency increase, the wavelength decrease. If the frequency decrease, the wavelength will increase. That's how you will score the 4 marks for this question. Is it clear? Then we have a question. Why slope is constant in the previous question? It shows that it was moving with a constant speed. If it was accelerating, then why this slope is constant here? This part, it shows that the car was continuously moving with a constant speed. So you are at point X when you're observing a car. It was say moving at a speed of 30 kilometer per hour. So, and it is moving away also at a speed of 30 kilometer per hour. That's why this slope is constant, the change in the frequency. If it was like a gradient was increasing, it means the change is increasing. If gradient decrease, it means the speed will decrease. Figure shows the ultrasound detector. So ultrasound detector, the estimator is held. As you can see, the estimator is held against one wall. It emits the pulse of ultrasound and detect them when they return after reflection from the opposite wall. So the ultrasound basically like sensors they send and then bounce back, or you can also use to bounce back, but it is reflected from the opposite. Explain why the ultrasound must be emitted in pulses. So why we use a pulse? Why not like a complete continuous wave? Because look, when we use a pulse, we can distinguish between the one which we send and one we receive. Say this is representing example, we are sending the pulse and then it bounce back. So if we are sending a continuous wave, it will be difficult to identify the wave which is sent and which wave is received. So that's why we don't use continuous wave. What we use a pulse. Pulse means like wave or a small signal or less than one. So that pulse will travel And when pulse strike, it will bounce back. So when we receive pulse, we send another one. So why ultrasound must be emitted in pulses? So what is the reason for that? So we can able to distinguish between the one which is sent and one which is reflected. Otherwise, if you are sending just a continuous wave, it will be impossible to detect the one which is sent and the received one. Because if the stationary is there, like if the object is stationary, say we are sending a pulse of 30 hertz or 30 kilohertz. So we receive also a frequency of 30 kilohertz. How you can distinguish that which one the send and which one is the receive one? It's impossible to identify that. So that's why we never use a continuous wave. We use a pulse. So one pulse returned before the next one is emitted, or to able to distinguish between the reflected and the emitted one. So we can distinguish between the wave which we are sending and the wave which we receive. The pulse or a signal sent and reflected. So that is the main idea of sending. This is a very common frequent question, that why the waves must be sent in pulse in a pulse echo technique. So we can distinguish between the pulse send or the receive, or you can also say that we can, so one send and the other receive, so it will not interfere with each other. So one pulse return before the next one is emitted. Is it clear, this one? Then the next one, the shortest distance estimator can measure a 40 centimeter. Calculate the longest pulse duration that would allow this distance to be measured. The speed of the ultrasound is 330 meter per second. So what we need the longest pulse duration, like how long or what will be the time taken by this pulse. So first we will use a formula that speed is distance over time. And using that, we'll estimate the time. Or because the shortest distance between the estimator can be measured, that is 40 centimeter. We have to calculate the longest pulse duration that would allow this distance to be measured. Like what will be the wavelength we should use, or what should be the length of the pulse? Pulse duration here, because they're asking for pulse duration, so you need the time for each pulse. Like, and it's of 3 marks, so we can use the formula, because the speed, the pulse is sent and it bounce back. We want the pulse duration, or we need the time. So this distance was 40 centimeter, as I mentioned. So it will be in meter, it will be 0.4 meter. But when we send, the pulse is sent and the receive. So what is the total distance? The total distance will be 2d. And time, the pulse duration, like length of a, that is t. And the speed at which the wave is sent, that is 330. So when we simplify this, 330 is equals to 2 into 0.4 divided by t. So if we need t, this will be t into 0.4 divided by 330. So 2 times 0.04, which is 0.8 divided by 330, that is equals to 0.0024. second. So this is the duration, like the pulse duration, the length of the pulse. Not length of the pulse, it's basically the time the pulse will take to go and bounce back. That's called a pulse duration. Like pulse is sent and the pulse received, that time interval is equals to 0.0024 seconds. Is it clear, this part, how to calculate the pulse duration? The next one, when the estimator is pointed at a slope as shown in the photograph, like you can see, first the estimator was placed here, so it was sending and then bounce back. So the pulse duration, we work out that pulse duration, but now they're saying that when an estimator is pointed at a slope as shown in the photograph, it is unable to measure the distance. Why it is unable to measure the distance? Suggests why the estimator is unable to measure a distance to the slope wall. Like the wall is having a slope and the distance is, we are not unable to measure that distance. So what might be a reason? Because the ultrasound which is reflected from a sensor and ultrasound reflected towards the, like it is actually making a certain angle. Like instead of, before that, when we point, so it travel, bounce back and return. But what is happening here, as it is inclined, so when it is making a certain angle, as a result, what will happen? The reflection will occur. And due to this reflection, this won't receive back by the sensor. So the ultrasound reflected away from a sensor and reflected towards the floor or the ground. It does not bounce back towards the sensor. That's why it won't be useful. Because this must reflect back so that we can estimate the distance. Then question 18, scientists arrange apparatus to test the Doppler effect. He arranged the trumpeter to play a note of one frequency on a moving train. Stationary musicians standing on a track listened as the train went past and compared what they heard with the original one. Explain how sound waves travel through air. Sound waves are basically longitudinal wave. Particle vibrate parallel to direction of wave and travel in the form of compression and rarefaction. So sound waves are longitudinal. The particles vibrate parallel to direction of the wave in series of compressions and rarefaction. So we'll have series of compression and rarefactions when the sound waves are passing. Then describe and explain what stationary musician would hear as a train travel towards them and then away from them. So like there is a train moving and the musicians are there on the track observing the sound which is they receive. So the question is, you have to explain this. It's the same question as we did previous in question 16. What about the spectator? The same answer is there. Like same answer we'll write, similar way. So we'll mention when the train is approaching the musicians on the track, the frequency which is received will be higher and the wavelength will be shorter. But when the train is exactly in front, then the frequency which is emitted out from the train, like the music which is played on the train, the frequency is emitted out. That note is same as what is received by the observer on the track. And when it move away from it, from position X, then as a result, what will happen? The frequency will be shorter and the wavelength will be longer. And the speed at which the wave travel won't change. As the frequency increase, wavelength decrease, or the frequency decrease, the wavelength will increase. So simple idea, when it is moving towards, there will be increase in frequency. When it is exactly in front, it will be same as the wavelength emitted out from the note which is played on the track on the train. And when it is moving away, so here when it is approaching, the frequency received will be higher. When it is moving away, the frequency will be shorter. At this one, the frequency emitted out from the train, like a music played on the train, is same as what is observed by the musicians. And if the frequency increase, the wavelength decrease. If frequency decrease, the wavelength increase. But the speed at which the wave travel does not change. Is it clear, this one? It's the same answer, no difference. So you will write in your own words. The Doppler effect and pulse echo.